Yeah, so I would like to review first some of the basics of plant lighting that growers and also developers and distributors of LED technology should be aware of. So there are 5 cardinal factors of plant growth. These are environmental factors, and they are all absolutely required for plants to complete their life cycle. The first one, of course, is light, the one that gives the energy and the signals for plant growth and development. The second is temperature, and we all know that unlike humans, plants cannot internally regulate their own body temperature. So they are completely at the mercy of the environment in which they grow. So that means in a controlled environment, you have to be very aware of the plant's needs in terms of temperature and address that. And then there are nutrients, the mineral nutrients, about 13 of them they get from water and the soil. There is the water itself, which provides the medium for the delivery of nutrients to roots. And water also is very important for maintaining the temperature of plants via its evaporative cooling mechanism in evapotranspiration. Atmosphere, I'm referring here mainly to carbon dioxide and to things like oxygen. In a controlled environment, such as a closed warehouse, you could have the best lighting environment in the world, and your crop might not grow at all if your carbon dioxide falls below a certain level. So you have to be basically addressing all 5 of these cardinal factors of plant growth. Again, each one of them is absolutely required. They are semi-controlled typically in greenhouses, but they need to be totally controlled in indoor or vertical farming. And unfortunately, they are very interactive, so you can't, quote, optimize one of them without considering all of the rest of them. And if you do optimize light, for example, at a given temperature, nutrient level, water, and atmosphere, you're going to have to do it again if you change any one of those. And so this makes optimization a very complex research process. So the light recipes that you hear various growers advertise probably are very tentative. They should actually be growth recipes defining the light in terms of all of the other combinations of cardinal growth factors. Now, just to review the dimensions of plant lighting, the light quantity or intensity is what is responsible for the increase in plant biomass during growth. The light spectrum or quality is what controls the development or the morphology of the plants. And the duration of the light in a given day, or the photoperiod, controls many aspects of development. One example would be flowering. These things do not act alone. Light quantity also affects quality and duration and all the rest. So they are totally interactive, all 3 of them. And so you've got to be very aware of where you are at on the dimensions of plant lighting scale. A few definitions. You see colored photons coming down into a square meter. They look like gentle snowflakes falling on a spectrum. Actually, they're coming down at 186,000 miles per second, and we have several definitions. Within the electromagnetic spectrum, plants utilize, within the visible range, the range from 400 to 700, which is known as photosynthetically active radiation, or PAR. And in the last year, it's been suggested that far red radiation be added to that. And so It's up for proposal right now, modifying PAR up to the 800 level. And if you do that, then photosynthetic photon flux or photosynthetic photon flux density, measured in micromoles of photons per square meter of absorbing surface per second, actually becomes TPFT, if you want to include the far red. That's the current designation that's being used. What's really important is this thing called daily light integral. Plants integrate light over the entire day, and so instead of expressing that as micromoles, what accumulates over the course of a day is moles of photons per meter square per day. And a lot of crops get categorized by their DLI requirements, especially for the greenhouse. We haven't gotten that far so much yet with vertical farming. One thing you should not use are the photometric units of lux and foot candles. These are luminous efficacy. I see that my graph got shifted. That yellow bar should be in the middle with the 555 nanometer max. And this is really the maximum absorbance of the human eye. So don't use foot candle meters to measure light intensity for plants. Here are some sensors and metrics of interest. The green one, which looks kind of square, is the total PAR. It is counting the photons from 400 to around 700 nanometers. And so that micromoles per meter square per second is an integrated value. Others of interest with plants are red and far red, and there are sensors that have been developed just for reading those and calculating their very important ratios. Now, if you look at a Spectroradiometer scan, this is a more expensive device, and it measures not only the photons, but the energy of the photons, and it kind of integrates those. So on the graph on the left, the green graph across the PAR and down into the UV and into the near infrared is solar. And you see that there's a rising amount of solar coming up into the blue and the green. It peaks at the red and starts to trail off into the far red. And the red line shows the relative energy. So the shorter wavelength blue has more energy in it than the longer wavelength red, for example. This is a very important graph here. The black line is what we call the relative quantum efficiency of each of the wave bands in the PAR. And you can see two peaks. One is a broad peak in the red, which goes from 600 to 700, and it has a peak at about 660. But many early LEDs were also around 620 to 630. They group plants pretty well. There's a secondary peak in the blue, which is from 400 to 500. And then surprisingly, there is relatively good, but a little bit reduced efficacy of green light from 500 to 600 roughly. So even though chlorophyll A and B don't really absorb green light, plants do. And that's because they have carotenoids and other accessory pigments that are contributing to that. So we can't discount green light in plant lighting. All right, now here is the very important reversible Phytochrome pigment system. The PR, the inactive form of Phytochrome, maximally absorbs red light around 663 nanometers, and then the PFR form, which is actually the physiologically active form of Phytochrome, maximally absorbs around 730 nanometers. And these can go back and forth because if you're giving plants white light, you've got some red light in it, you've got some far red light in it. And so what you're going to end up with is a phytochrome photoequilibrium, and the value of that is going to determine a lot of aspects of plant development, whether they will flower or not, how they will grow, for example, whether it'll be shade avoidance or compact growth. Very important in plant photomorphogenesis. And then I add another one, the peak of the blue absorbing pigment, cryptochrome, which is important for stomatal movements. Blue light opens the stomates on leaves typically, and other things like phototropism and others we don't even know yet. So there are some of the plant-centric pigments, with the dotted line, again, being the luminous efficacy for the human eye. So you can see it's not all that important. All right, and then, yeah, so put in a few discrete red, far red, and blue LEDs to show how you can focus on peaks of those and to specifically control plant development, especially if those channels are individually dimmable. Okay, and finally on this basic thing, the relative absorbance, transmittance, and reflectance of the various bands of light. The blue from 400 to 500, it's mostly absorbed. So coming through a multi-layer plant, the first layer is going to get most of the blue. Just a tiny bit is reflected. For the green, between 500 and 600, a little bit of transmittance, a little more reflectance, but still pretty good absorbance. But it does allow secondary leaf layers to absorb more of the green for photosynthesis. And then the red is similar to the blue in terms of transmittance and reflectance. The far red is the interesting one. A lot of it gets transmitted through leaves, a lot of it gets reflected, and that little horizontal band of gray is the amount that gets absorbed. So even though there is a lot of far red light in sunlight, midday sunlight, only a little bit of that is getting absorbed, and so that keeps the phytochrome photoequilibrium kind of high. Okay, let me transition over now to issues of sole source plant growth lighting. And the big difference between indoor agriculture and greenhouse supplemental lighting that we were talking about this morning is there's no free solar light contribution. It's all sole source lighting. And there is no competition for LEDs in that space. LEDs are the only non-heating plant source that can do this. And for that reason, we want to keep our electrical energy bills as low as possible, so we go with the lowest PPFD or TPFD and the lowest DLI for indoor ag crops that we can. Okay, that's really important. And it turns out that the spectral quality of the light that you grow plants indoors under is much more important than it is when it's supplemental lighting in the greenhouse. At higher light intensities, plants translate blue, green, red, and now maybe a little bit of the far red into PAR. They just use it mostly for growth, except at the end of the day. But for indoor, you can set spectra to get desired plant responses throughout the day, throughout the production cycle. And that's important also. And so there's an opportunity to create specialized light recipes, and I would actually say growth recipes, because you can't ignore the temperature, the nutrients, the water, the other things that the light interacts with so importantly. But it gives an opportunity to create and to also look at phasic optimization. Does a plant require the same intensity and spectrum when it is a seedling as when it's a baby green or a teen green or a mature leafy green? It could very well challenge. And so this is going to be a challenge for future LED developers for plant growth lighting. Here's a picture I took. I think I did it in 1991 at one of the first indoor farms in DeKalb, Illinois, Phyto Farms of America. They had moving conveyor benches coming at the camera, very, very slow, but they were using 1,000-watt high-pressure sodium and metal halide lamps that were water-cooled so that they didn't cook the top of the crop. But Phyto Farms eventually had to close its doors. The price point they could get from the Chicago and Milwaukee markets could not keep up, even with off-peak electrical power rates they were paying. The more than 1 megawatt of power draw that they had within that warehouse was making it impossible for them to be profitable. And so that's what happens with high-intensity discharge. It just doesn't work indoors completely at all. Okay, in Japan, Kozai out of Chiba University started the vertically stacked plant factory concept, at first with white fluorescent lighting on the left, but then when NASA sponsored the first plant LED experiments more than 20 years ago, actually in the United States, LEDs started to take off in terms of a possibility for growing plants indoors without a lot of extra heating. And so on the right is one of Chiba's first multi-tiered plant factories using LEDs. Now, the little history here. Here's from the first publication, and there is the emission spectrum of the red LED that they were growing seedlings under initially at first, and then they thought, well, we might need a little bit of blue light, but they didn't have enough efficiency from blue LEDs yet, so they used very small fluorescent lamps. And what they found is that the plants grew stockier and stronger, but that the hypocotyls, they were shorter and shorter the more blue light they added. So they found that a few blue photons were really important, but not too much, or it actually was suppressing the plant growth. So then at the Kennedy Space Center, after that, they started adding green monochromatic light to the reds and the blues, and they grew okay, but without the green, they couldn't see the true color or the stress health status of the plants. So when they added the green, like on the right, the plants looked more normal. And not only that, they grew better. So the RGB treatment you see there, your leaf area, your shoot fresh and dry weight, were significantly higher than all the rest. And so this at first was surprising, but you know, it really isn't. If you think back to that relative quantum efficiency curve, all of those wave bands in the PAR are contributing. And so and sometimes it's synergistic in ways that we don't even know yet. So you can see we are gradually rediscovering the value of white light in doing monochromatic LED research. And then Gary Studi, also at NASA, came along with, he grew a reddish type of lettuce called outrageous. It's actually grown in space. And he found that when he grew it just under red LED light, it was green. Only if he added a little blue could he bring out the anthocyanin component, the pigment. And of course, the anthocyanins also are antioxidants, and that got the whole thing going about phytonutrients and their control with different qualities of light. So, the reasons for the spectral composition of LED arrays, red dominates. And when you get into plants like lettuce lettuce is a red-loving species. It drives photosynthesis. You get more stem and leaf elongation. Blue has a lot of complex effects. It can be very important, as you can see from the list of bullets there, including promoting pigment, antioxidant, and phytonutrient accumulations, but you don't want to use too much of it. But you may want to use more of it at some stages of the life cycle than at the other. And then adding far red, there's a lot of current interest in far red. It definitely promotes stem elongation, leaf expansion, and in long day plants, it promotes flowering. It shifts that phytochrome photoequilibrium to less of the active form, and that makes long day plants flower. Recently, it's been found that 700 to 800 nanometer radiation, far red, also stimulates photosynthesis, but not when it's applied alone. It has to be applied in combination with shorter wavelengths of the PAR, the 400 to 700. UV, LEDs exist, still quite expensive. It prevents intumescence or tumor-like growth that occurs on some plants when they are grown under very low light intensities, especially without UV. Intumescence is a strange thing. It can be affected by red-far red ratio. In some species, blue light alone can prevent it. In other cases, you do need UV. Green, I've been developing that for you. It has some applications. So when you add all these up, if you had them in one array, they would be white. So are white LED answers, are white LEDs the answer to the issues that we're having here? There can be phosphor-coated ones. There are color mixing optics, potentially. But to me, the biggest justification for white LEDs is because that's what plants evolved under solar light in the environment. So they have the genes, they have the products that respond to broadband and full spectrum light. So let's look back a few years. Here is an experiment conducted in Bruce Bugby's lab where they compared the effect of 3 white LEDs on soybean growth. And on the left, you see the comparative spectra. The solid line with the highest blue peak, that's the cool white. It's the bluest one. And you can see how the plants look in the compartment on the far right. They are very short with the smallest leaves. They also have the smallest biomass. Then the neutral are the dashed lines. It looks like there's a shift. The blue is lower. It shifts more toward the red. And that's the middle compartment, and you can see they're a little bigger. And then finally, the warm white, which has the lowest blue peak and the highest and more red-shifted red peak, and those plants are the largest. They would be the ones in the left compartment. Then you can also see the seedlings in the cotyledonary and also in the first primary leaf stage, going from warm white, neutral white, down to cool white. So a real dramatic demonstration of, even within white LEDs, how you can get growth regulation. All right, at the beginning of the 2000s, Haight's law came out, and they projected that over the course of decades, there will be a reciprocal trend. The efficacy, the efficiency of the LEDs would go up, and the cost of them would come down. And yeah, that occurred for a while, but that hasn't been republished since almost 20 years ago. However, PPEs, the photosynthetic photon efficacies, are going up. In 2014, the best PEs for plant growth were were between 1.7 and 2.3. Well, they're a lot higher than that now. And here is a projection on the right graph, the middle graph, which is photosynthetic photon flux. They're projecting that by about 2030, both the phosphor-coated and the color mixing LEDs are going to be a lot higher in photosynthetic photon efficacy compared to the HPS, which is stuck down there at about 1.8. Well, HPS is a non-issue in indoor ag, but I show that to you for completeness. The important thing is that the efficacy of LEDs continues to go up for now. And that's going to be really important for getting the best bang for your buck as a grower. So the sole source lighting needs, if we summarize them for the indoor farming industry, continued improvement in PPE is needed, continuous decline in capital cost of new LED lighting equipment is needed, and it's happening. I think down the road, we want to look at optional waveband dimmability for multi-channel monochromatic on broadband LED arrays. Light prescriptions, including spectrum, irradiance, duration, and timing for different crop species, for different cultivars within a species. And in combination, of course, with optimizing environments of the other cardinal factors. As well as automated growth detection and LED switching for targeted lighting. All kinds of things you can do with light distribution, not just with spectrum, but we will not be losing photons out of cropping areas, and we'll be recapturing photons that are lost due to angular beam spread. So lighting architecture will also become important. And finally, these recommendations, and they all seem to point toward broad spectrum or full spectrum lighting with potential for spectral selection and dimming in the future. And with that, I will stop talking and we can convene our roundtable.